Welcome. This is some quick update on analytic torsion for graphs. I have all the definitions here. Some work done on Martha's Vineyard. We had some good time there, and I was, rather than polishing some old stuff, I was kind of pushing this a little bit. It's a beautiful topic, and I made some progress, and I can prove now this experimentally seen, numbers for analytic torsion. But let's look at the definition. So first of all, everything is defined for arbitrary graphs, arbitrary finite simple graphs, arbitrary networks. Doesn't have to be a manifold. And there's a notion of contractibility, which tells that a graph is contractible if you can take away one vertex such that the unit sphere is contractible, and also then the rest is contractible. So this is not a contractible graph here. Also, this is not contractible. You cannot take anything away. So this is a sphere. This is not a sphere. This is we look always at the Whitney complex, at the complex set of finite non-empty sets which are given by vertex sets of complete subgraphs. So that's Whitney complex, and it's a very natural simplicity complex attached to a graph. And so the notion of contractible is a recursive definition. Also the notion of a sphere, M-sphere, is recursive, use contractibility. So a sphere is a graph such that you can take away one vertex, such after that it becomes contractible. Indeed, if you take away any of these vertices, it becomes contractible. It's a wheel graph here in this case. And so that's not a sphere here. It's not happening in this case. And we also want that every unit sphere is a n-1 sphere. So in this case, it's just dimension less. So in this case, when you take that away, you get the circular graph. So a two-sphere is a graph such that every unit sphere is a one-dimensional sphere, which means it's a circular graph with 4 or more vertices. So that's notion of a sphere, and so they are very kind of the most basic objects in graph theory. So contractible graphs can be wild. Spheres are kind of, you have a manifold structure here. And then we have the Dirac operator, which is a matrix, n times n matrix, if you have n complete subgraphs. And this is made of the exterior derivative here, which is the lower part, and then the transpose of these exterior derivatives. These are 0, 1 matrices, 0, 1, minus 1 matrices here, and also here. So this Dirac matrix is a very natural object attached to every graph, and so what we have is then the dk plus 1 is always 0, so the image of dk is in the kernel of dk plus 1. So we have cohomology. So this is like the gradient here, the gradient, and the d1 is actually the kernel, and so d1 of d0 first, and then d1, the curl of the gradient is 0. The diff of the gradient is the Laplacian. In this case, it's just that's a 0-dimensional Laplacian. It's the Kirchhoff Laplacian introduced very early. So all of these notions essentially have been introduced in the 19th century already. So then Poincaré, etc. So everything has been kind of become more abstract in the 20th century, but it's very, very simple linear algebra. And then we have the Hodge Laplacian, which is the square. That's actually came very late, only that you look at things like this. Poincaré was not actually looking at this matrix as a whole, but he looked at these matrices kind of by themselves. If you look at the whole thing, then you have just one n times n matrix, and then you square it, you have an n times n matrix which has these blocks, which are the Hodge blocks, and these blocks are very important because the kernel of these blocks are the harmonic forms, the k-harmonic forms, and the dimension of the kernel is the Betti numbers. So the Betti numbers of a contractible graph is just 1, 0, 0, 0. There's always the constant harmonic function on a graph, which is here always L0, always has a kernel. In the case of a sphere, there is only L0 as a kernel and L, the last one, has a kernel too. It's related to the fact that you have kind of some duality here, kind of in this case. That's why also this works here in this case. But it's analytic torsion is a more subtle thing. So first of all, about the definition of analytic torsion, it's a linear algebra notion. So you take this the pseudo determinants of this LK, and you take the odd ones and you put them on top, the bottom ones you put into the denominator, and then you also have this K. And that was actually something which puzzled me for until really this winter in Martha's Vineyard. It became clear to me why this is actually happening. It was not clear to me. It's a linear algebra story, and it's kind of a strange thing. Why do you put this K here? Why is this an interesting notion? So first of all, there's a hint about this. Depending on whether you have even or odd part, you put them in the denominator or nominator, and it's kind of the analog of the super trace is the analog. The super determinant is the multiplicative analog of the super trace. And so when you look at the LK and you take the super trace of the LK, so you take L0 divided by the determinant of L0, super determinant and the pseudo determinant of L0 divided by the pseudo determinant of L1, etc. This is universally for every graph, this is always 1. And that's a very important symmetry which I've used a lot. And it's the McKean-Singer symmetry, which is a supersymmetry, and it usually is written down like the supertrace of the heat kernel is the Euler characteristic. But it's just a consequence that the supertrace of L to the K is always 0 for every positive K, and so only supertrace of 1 is not 0. That's the general, that's the Euler characteristic. So that's a kind of a beautiful relation which kind of shows that you don't look at the supertrace of L. The supertrace of L is not interesting because of this symmetry, because of this universal symmetry which you have for any network. So it's very nice. And now what became clear to me only when I actually, not experimentally, this needed also some literature search. There is a theory of determinants of chain complexes, which is kind of introducing also this kind of, call it just determinant, but it's actually a super determinant of a chain complex. And what was not clear to me is kind of, you know, until this winter when I saw this opened the whole thing, is that you can also look at this Dirac block. So this is the Hodge-Laplacian, right? If you look at the Hodge-Laplacian, so if you take the d square, you have two parts, you have this and this. So it is not absolutely not clear that this is actually, when you look at the determinant of LK, that it's actually the determinant of this, pseudo-determinant of this times the pseudo-determinant of that. But that's just essentially rephrasing that the kernel of dk is the image of dk minus 1 is included in the kernel of dk. And then you can actually just write down a linear algebra as a statement about matrices, which tells, and that's kind of the important thing, it tells you that actually if you take these Dirac blocks instead of the LK blocks, then you have a much nicer situation. So I was kind of stuck with, first of all, with this, and second of all, also with a geometric interpretation of the pseudo-determinant of LK, which is not so clear what this is. But once you write it down like this, so if you write it down using these Dirac blocks, so the Dirac blocks here, which uses this, these are rectangular matrices here, these are the Poincare introduced them, these incidence matrices. One of the basic things, first things one has done in algebraic topology is introduce these matrices. And now you can look at these are symmetric matrices now, and what happens is, and that's the key thing, is that the superdeterminant of D, which is kind of, it's just the determinant of D0 divided by the determinant of D1 times the determinant of D2. Of course, these are all singular matrices, but you have the pseudo-determinant which is coming in. So pseudo-determinant are extremely important. And then you have this kind of very, very natural notion of a superdeterminant of the Dirac operator. Also, the determinant of the Dirac operator, pseudo-determinant of the Dirac operator is very interesting. So that's kind of a bosonic version of that fermionic version. So this is a bosonic, and that's fermionic. So in the bosonic case, these are huge. This counts. This counts, actually this counts trees, and this super counts trees. And super counting has just a chance that things are cancelling out, and these are much smaller numbers in general. So they are in general, even for small graphs, you have hundreds and hundreds of digits of which come in when you take the determinant of D. So I was studying already before 2015 when I made this experiment. I studied just the determinant of D, kind of see what happens. But I didn't make much progress. But in 2015 I measured this, and I mentioned this in December. And what I was looking at first was the case of a two-sphere, which is very, very interesting. The case of a two-sphere is actually very beautiful, because in the case of a two-sphere you always measure, it's the number of the analytic torsion is the number of vertices divided by the number of faces. So that's always what you see, and you can see this also. So there are two ways, two symmetries which come in to see this. First of all, it's the supersymmetry of McKean-Singer, which allows you to see that that's actually kind of, when you write down the torsion, it's the determinant of D0 over the determinant of D2. Now the determinant of D0 over the number of vertices, that's the number of trees. The pseudo-determinant of D0 is the number of rooted trees in the graph. And when you divide by the number of vertices, then you get the number of trees. And what already in the 19th century, Van Stout has actually used this for the proof of Euler's gem formula, famous formula which says the number of vertices minus the number of edges plus the number of faces is equal to 2 for two spheres. That's what you have always. And so what happens is, if you look at the dual graph here, in this case, is a cube graph. That's a one-dimensional graph. It doesn't have any triangles. So what you have is, you count the number of trees here. The number of trees here is the same than the number of trees here. That's actually kind of gives you then immediately the proof of the Euler-Gem formula. That's how Van Stout was doing that. But this is essentially this theorem for two spheres is essentially kind of using this kind of Poincare duality or duality which you have for polyhedra, and also this supersymmetry, which is also I was looking at the two-dimensional case in December. That was kind of just a Christmas Eve or Christmas Day. I kind of realized that why this works. But the three-dimensional case already kind of eluded me, and I had no way to actually get this using this definition. So there's an appendix in this book which kind of introduces the determinant of a chain complex. And so let me just explain this. So first of all, we have this Dirac blocks, which you have. You look at these Dirac blocks, and what happens is kind of a very important thing is that I didn't write that down. It's actually the determinant of LK, superdeterminant of LK, pseudo-determinant of LK is the pseudo-determinant of DK times the determinant of DK minus 1. So that's actually the key. That's actually the key. Just kind of, I should put that here. So that's actually a nice thing. So instead of kind of computing these determinants of LK, which is a product of this column, the transpose of such a column, Dirac column times the Dirac column itself, we can actually write it using the decay. And now that's extremely important, because the pseudo determinant of decay has a geometric interpretation as a tree, counting trees in a k-dimensional trees. And that actually then explains the whole thing, because what happens is when you, for example, take two graphs and you put them together and with a contractible intersection, so you have this valuation property. You count in the right way. You count things. But this this analytic torsion is very, very subtle. So if you add some things to, for example, you add another tetraeder here, you completely destroy the whole thing. But there are three results which I can kind of understand now. First of all is the contractible case, even more general homotopic to one. The second case is the even-dimensional sphere. The third case is the odd-dimensional spheres. So, for example, for circular graphs, if you take a circular graph with n vertices, then you get n squared. Analytic torsion is just n squared. And this is kind of the contractible case, for example, applies for complete graphs. If you take a complete graph with n vertices, then the analytic torsion is just n. Now, so that's the key. The key thing is this lemma, which says that you, instead of taking this k, right? If you take this k, what happens is, why do you kind of take L0 to the 0, L1 to the 1, L2 to the 2? Why do you take this times k? But what happens is, if you just you write them down and you arrange things, it's actually the same. Using this identity here, you see it's the same thing than the superdeterminant of the Dirac matrix. So I should also say that classically one usually takes the square root here of this definition, and the reason is that that classically the notion has only been really kind of been studied really for odd-dimensional manifolds. In the even-dimensional manifolds, it's actually zero. So when you take barycentric refinements of a two-dimensional situation, what you actually get here, this goes to zero. And in this case, if you take the square root, that's kind of like the volume. You have to divide by the volume. So there is in classical situation, you have more overhead, you have more things. Usually you have even a representation of the fundamental group in some orthogonal group or some unit in a field. All kind of crazy mathematics is coming in here. This is very, very simple, very basic. It's a functional on all graphs. You can study it for any network, and you can see whether you can understand. You would try to understand what actually these notions are. And I still don't understand for most graphs what actually happens here combinatorially with this. Even if the situation is simple, like for example for an analysis, the numbers are getting crazy. Or for a genus 2 surface, this analytic torsion gets crazy. So there's no relation anymore with the f vector of any, or seems to be kind of no relation with any f vector. It's again super counting trees, but the trees are becoming more complicated. So it's very interesting. I think the research about this will continue for quite a while, because this is just the beginning. This is a tip of an iceberg. But it's those situations where you really can compute this. So V hat here, that's just the number of maximal simplices, facets, maximal simplices. So in this case, there's 6 faces. In this case, it's actually one-dimensional graph, so you have 12 facets. So this is not the face. You wouldn't need CW complexes to actually describe this as a two-dimensional surface. So let me just explain a little bit about the proof. So first of all, what happens is these matrices, when you look at the Hodge-Laplacian, for example, if you look at the Hodge-Laplacian and you then the L0 always has a kernel. In the case of the sphere, also the LR has a kernel. Now, if you shave things away, if you take away the first column here, that happens in the contractible case, then you get something, the Hodge case, you get something which is invertible. And also in the sphere case, if you take that away, you get something invertible. So it's kind of with this shaved version, this is actually equivalent that the superdeterminant of this shaved version is equal to 1. But that only works in this case when you have this. In the case when some other Bethe numbers would be 0, you would have to, would be not 0, like in a not simply connected situation. You have to look at there are other things which come in, and that's maybe why it's called torsion, because it really matters what happens when you have a non-trivial fundamental group. So that's the thing. And then once you kind of the second thing is this beautiful Cauchy-Binet formula. It looks like a small thing to generalize Cauchy-Binet to the case of the singular case. So the usual traditional Cauchy-Binet formula is this formula when you have maximal rank, and I looked at it when you have when these are determinants here, and I looked at it when you have pseudo-determinants, which is not quite obvious, because when you have pseudo-determinants, they don't satisfy the usual Cauchy-Binet formula. The superdeterminant of A times the superdeterminant of B is not the superdeterminant of AB, right? So that's it's not obvious how to, but there is this generalization, and this is what I did in 2013. It was published in 2014, one of the cases which I really bothered to get it published. And so I worked this summer just to clear it out, bringing it ready for publication, because I think it's kind of just a one in a lifetime opportunity that you can prove something very fundamental which has not been proven before. And most of the work was really about realizing that it's not. Looking in all the linear algebra books, look at all the sources whether this has already appeared. So it looks like a small matter to go from determinants to to pseudo-determinants, but pseudo-determinants are really very important in this framework, because these matrices are in general non-invertible, and in this case with the decay they are even non-invertible in this situation. So it's still kind of, in this case, these decays are singular. In general, all of them are singular, and you have to, but you can describe them in terms of trees. So the superdeterminant of L0, for example, is the number of rooted trees and in the graph. And then when you divide by V, then you have, so this is the number of, when you divide by V, this is the number of rooted trees in the one-dimensional. Actually, we have triangle-free graphs like this, graph without triangles. It's one-dimensional where you have only D0, you have only two blocks here and one Dirac block. In that case, you have this is the number of rooted trees, and if you divide by V, it's the number of trees. So every vertex can be a root, so that's why you have this number. And so that's it for today.